In this video, we'll be looking at capacitors and capacitance. We're looking at what capacitors are, how they're made, how they work, and some of the uses we put them to. A capacitor is a component that stores energy in the form of an electrostatic field and is able to oppose any change in circuit voltage. There are several types and ratings of capacitors, and as you can see here, they range from very small to very large. In its simplest form, a capacitor is simply two metal plates with an insulator between them. The insulator we call a dielectric, and it can be many things: air, glass, plastics, etc. We'll look at them shortly. Capacitors can also, instead of being flat plates, they can be rolled up to give us a greater surface area for the size. Capacitance is measured in farads, where 1 farad is if we have two plates with 1 volt across them, and that is able to store 1 coulomb of charge, where a coulomb is 6.28 times 10 to the 18 electrons. And capacitance can be found, capacitance in farads is equal to the charge in coulombs divided by the volts needed to put those coulombs there. For example, if we have 12 volts across a set of capacitor plates, and that enables us to store 6 millicoulombs of charge, then our capacitance is 6 millicoulombs divided by 12, or 5 times 10 to the minus 4 farads, in other words 0.5 millifarads. And that is quite small, which is common for capacitors, because 1 farad is in fact a very large unit, a very large value. The charge stored on a capacitor is proportional to 3 things: the area of the plates, the distance between them, and the type of material that's used as the dielectric. The area of the plates is proportional to, or the capacitance is proportional to the area of the plates. In other words, the bigger the area, the bigger the capacitance, and vice versa. Whereas capacitance is inversely proportional to the distance between the plates. So if we have a bigger distance, we have less capacitance. And permittivity is a number. It's just given a number. If it doesn't have any units, it is normally related to a vacuum, is given the number 1, and everything else is compared to that. It's either better or worse than a vacuum. So the total capacitance is found by the formula permittivity times the area divided by the distance. And here is an example of permittivity that is for some different materials. So a vacuum is given 1, air is very close to a vacuum, and for example glass has a relative permittivity compared to a vacuum of 5. In other words, if we had a glass dielectric, it would that capacitor would store 5 times the amount of charge of an air capacitor. Various types of dielectric. So we have polyester, ceramic, tantalum, and electrolytic. So capacitors are often categorized by what their dielectric is. So we say is a something or other value polyester capacitor. The way we can increase the value of capacitance is by having multiple plates inside the one capacitor with dielectric interleaved between the plates. So for example, a ceramic capacitor, the one side would be connected to one of the output legs, the other side to the other output leg, and so we have multiple areas for our capacitance to go. The electrolytic capacitor is slightly different in that the dielectric is, or the insulating part is in fact a metal oxide layer, and there is also normally some tissue paper in there which is soaked in ionic solution to give us conduction between the plates. For electrolytic capacitors are often made with aluminium foil, and so we have an aluminium oxide on the capacitor. You also see that most electrolytic capacitors are polarized, as indicated by normally having one leg longer than the other, the long leg being the positive. However, that's not always the case, so you have to watch them very carefully. A lot of electrolytic capacitors have markings on the side, as these ones do here, showing us which leg is the negative leg. Some capacitors, of course, are also surface mount, so they're really, really small, and they will have some other marking on them to indicate that. We also can have non-polarized electrolytic capacitors specifically designed to work with AC circuits. For an air capacitor, where we use air as the dielectric, these are not very common nowadays, but they were very common when we had AM radios, and they were used as the tuning circuits, where we had one stationary set of plates and one set of plates that rotated on a shaft, and the area that was in mesh with each other was the area of the plate. So any area of the rotor that was outside the stator wasn't counted in the area. And so here's an example of one where we have multiple plates, a tuning knob, shaft, and this is the rotor up here that would be rotated down into the plates. And here's a circuit where one was used in a very, very simple, one of the most simplest of radio circuits. But as I said, not very common these days. The value of capacitance differs with the type of capacitor, and so ceramic capacitors tend to be very small values, from the picofarad to the millifarad range. Film capacitors in the middle here, and electrolytic capacitors are the ones that have the biggest value, often going up to, in fact, thousands of microfarads. And we select the type depending on what our application is. Larger capacitors are able to have their values written on them. For example, here we have 10 microfarads and 50 volts, and which side is our negative. The symbol for a polarized capacitor will normally have a plus sign on the positive side, and the negative side will have show a curved plate. Smaller capacitors, so a little ceramic capacitor, which might only be a tenth of the size of this, will often have a number code written on it, and the value of the capacitor is this number here, which tells us its value is 1, 0, and 4 zeros, and it's measured in picofarads. If it's got this sort of a code on it, it's always in picofarads. So the value of this capacitor is 1, 0, and 4 zeros in picofarads. And then we have to convert that. For example, that would be 0.1 microfarads. Other numbers, for example, the maximum voltage rating is given a code over here. We see 2E is 250 volts. The tolerance is K, and that, if I shift out of the way, K we see is a 10% tolerance. As I said before, capacitors range in size from 1.5 to 2 millimeters right up to very large, but often the size of them varies dramatically depending on not only the value of capacitance in farads, but also the voltage. Right, so this one can only handle 20 volts, but it can store 45,000 microfarads. Whereas this one can only store 220 microfarads, but it can handle 200 volts. Some of the uses that capacitors are put to, for example, energy storage, power filtering or conditioning, and power factor correction, used in large AC circuits, motor control circuits, etc. High pass and low pass filters, so we use them in audio circuits or other circuits where we want to change or filter different frequencies out. We use them for filtering noise out of circuits and AC circuits or main circuits. These are sometimes called snubber circuits. And we use them also for motor starting, where if we have a single phase motor, for example, we can have a second set of windings with a different to set a phase rotation. And we use capacitors for that, as you'll be finding out when we look at motors and motor starting. A common use that you may see capacitors put to these days, here's a big capacitor here, and it's used to power the subwoofer, where we want to get a large amount of current quickly dumped into to power this woofer up. We need to use a capacitor because a battery just can't supply enough current quick enough. The energy stored in a capacitor is directly proportional to the voltage across the capacitor, and the area underneath that line is the energy stored in the capacitor, measured in farads, in joules, where the energy is equal to a half capacitance in coulombs, charge in coulombs times voltage. However, because coulombs is hard to measure, 6.28 times 10 to the 18 electrons, you've got to count fairly quickly. So we can, instead of using Q, we can use VC as from the earlier formula. And so we have the energy stored in the capacitor is equal to half the voltage squared times the capacitance in farads. Uses of capacitors, we can use them for smoothing DC. So as we saw before, when we rectify AC using a bridge rectifier, we end up with pulsating DC. If we put a capacitor across that DC, the capacitor charges up initially, and then when the voltage starts to drop off, the capacitor dumps its charge back out into the circuit to maintain the current flow and the circuit voltage. And so as it charges up, it recharges a little what it needs, and then discharges, recharges and discharges. And so this is DC smoothing of rectified voltage. And we can also use this, for example, in vehicle alternators, or where we just want to smooth out the DC. We're not storing it, we're just smoothing it out. Capacitor charging. So when a capacitor gets put into a circuit, we normally have to have a resistor with there, because a capacitor can charge and discharge extremely quickly, which would damage the wiring. So if there's nothing to slow or control the current is equal to the amount of charge over time, or the change in charge over the change in time. And a capacitor in a circuit will normally have some resistance in there to prevent excessive current. So the rate at which a capacitor charges depends on the size of the resistance in the circuit and also the size of the capacitor. So a small capacitor will actually charge up faster than a large capacitor for the same value of resistance. Now let's have a look at a capacitor charging. When a capacitor charges, so we turn our circuit on, so we have our EMF here, and we have electrons or charge will come on the plate, will attract electrons away from that plate towards the battery. Electrons will travel from our EMF towards this plate, and the amount of current will be limited by the resistance in the circuit. So in this case, when we initially turn our circuit on, we get maximum current flow, limited only by the resistance of the circuit. Initially, the capacitor offers no resistance, but as the capacitor starts to charge up, its internal resistance starts to increase, and therefore the current starts to decrease. And the capacitance builds, the voltage across the capacitance builds up, So as the voltage across the capacitor builds up, so for example, if we had a 12-volt supply and this started off as 0 volts across it, therefore the whole 12 volts would be across the resistor. But as the capacitor charges up and gets to 6 volts across the capacitor, then there would be 6 volts across the resistor. 9 volts across the capacitor, 3 volts across the resistor. And when the capacitor becomes fully charged, it doesn't allow any more current to flow from its or to its plates. Current drops off to 0. The voltage across the capacitor is equal to the supply voltage, and the voltage across the resistor, because there's no current flowing, will be 0. When we discharge a capacitor, so now once it's charged, we can turn that switch off and the capacitor will stay charged until we turn the switch on and start to discharge it. When we start to discharge it initially, so the whole, let's say for example 12 volts from our capacitor is across our resistor. So maximum current will flow, but as current flows, the voltage across the capacitor starts decreasing. Therefore, the current will start decreasing because there's not enough voltage to support it. And both the voltage and the capacitor, voltage and the current decay with time. And so the reason that we often use capacitors is because they can charge and discharge extremely quickly compared to a power supply. Now we have a thing called a time constant. So if a capacitor started to charge at a certain rate, if it stayed at maintained that rate of charge of its initial state, it would have got to the supply voltage in this time, at this point, and that time, and the amount of time it takes to get to that point, if the rate of charge was the same as its initial rate, is found by time is equal to the capacitance in farads times the resistance in ohms. However, it doesn't maintain that rate of charge. It slowly decreases its rate of charge, and after that time, of the time constant, C times R, it has in fact only reached 0.63 or 63.2%, to be a little bit more accurate, 0.632% or 63.2% of the maximum value. So the time constant of a capacitor is equal to RC in seconds. So if we had a 10 microfarad capacitor and a 100k ohm resistor, we multiply them together and we get 1 second. So after one time constant, it has reached 63.2% of the maximum value. In the second time constant, the same amount of time, it increases 63.2% of the remaining value. And in the third time constant, another 63.2% of the remaining value. And that's why it is a curved graph. Now, for practical considerations, we say that a capacitor has reached fully charged or fully discharged, for that matter, in 5 time constants. Although theoretically, if it's only changing 63.2% each time, it never reaches fully charged, but for all intents and purposes, we say after 5 time constants, it's either fully charged or fully discharged. So current flow is a maximum at the start of either the charge or discharge cycle, and the current follows the voltage in that it changes by 63.2% for each of the time constants as well, either increasing or decreasing. So here is a graph of current of a capacitor that is charging. And so initially we have maximum current flow limited only by the value of resistance. And after one time constant, it's dropped 63.2% or 37, dropped down to 0.37 of its initial value. And in each case, it drops, each time constant, it drops another 63.2% of whatever is left. Where a capacitor is used practically, they're used in timing circuits, especially in electronics, where so we have a little integrated circuit here, an IC, which is can be switched on and off, and it's going to give us a output, a square wave, depending on whether it's turned on or turned off. And we can control the output by having a capacitor and some resistors. And so as the capacitor charges up through one of the resistors, it reaches a certain point where this integrated circuit says, yep, I'm on, so it turns on, and then the capacitor discharges through one of the resistor network again until it reaches a certain value, and the integrated circuit says, yep, now I'm switched off, so it'll turn off. So we can change this charging and discharging curve, if you like, or sawtooth waveform as it's known. We then change that to a square wave output where it's either fully on or fully off. And the speed at which that charge happens is related to the value of resistances and capacitance. A more common use that we see as electricians for capacitors is a radio frequency interference or electromagnetic interference suppression. So for example, in big power equipment that have commutators and brushes, where they create sparks, and so we want to be able to limit the amount of interference that they put on the line. And so we have this little device in here which has got 3 capacitors inside it to suppress the any voltage spikes. When we use capacitors for RFI suppression, there's some rules according to the New Zealand wiring rules that we need to follow. And they are firstly that a capacitance connected to exposed metal is not to exceed 0.005 microfarads. And that is so that we don't have excessive current to the frame. And also, devices are not to be connected in the earth of a earth continuity conductor, so that they don't interfere with the protection devices like RCDs. We don't want, if there's current flows in the earth, we want that to happen so that our protection devices operate. And also, if we are replacing suppression capacitors for 230 volt appliances, they must be rated at least double that, right? 460 volts, and often you'll find they'll be 600 volts or better they will be rated at, and that's in accordance with our wiring rules. And that is capacitors in a nutshell.